In Chapter 8, we're building on the complexity that we've set up so far in the semester, and in Chapter 8, we're getting into hypothesis testing. In Chapter 8, we're only covering 8.1 and 8.2. So in 8.1, we're going over the basics of hypothesis testing, and then in 8.2, we'll apply what we learned in 8.1 and go into testing a claim about a proportion specifically. We're getting into longer sections here, so we're going to break up these sections, but I'll clearly label everything so you'll know where everything is. And for 8.1, let's go through the key concepts now. So as mentioned in this section, we'll go through key components of a formal hypothesis test. We've done a lot so far this semester. This is another really big important concept in the realm of statistics. So in 8.1, also as mentioned, the concepts in this section are general and will apply to hypothesis tests involving proportions. We'll go into that in 8.2. This could also be applied to means and standard deviations or variances. Let's start to lay the groundwork here for 8.1 and go into what is a hypothesis and what is a hypothesis test. So a hypothesis in statistics is a claim or statement about a property of a population. You've probably seen this word used in science before, so in chemistry and biology. In statistics, we can also use this idea of hypothesis. And as mentioned, we're making a claim or statement about a property of the population of interest. So then, based on this definition of a hypothesis, then a hypothesis test, which could also be called a test of significance, is a procedure for testing a claim about a property of a population. So we can form a hypothesis about a property of a population, and then we can test for that hypothesis, see if it's true, see if we need to reject or accept our hypothesis. We're going to use this example throughout all of 8.1, so you'll see it come back throughout the section. So our example here is a majority of consumers are not comfortable with drone deliveries. Some numbers here: out of 1,009 consumers that were asked if they are comfortable with drones that deliver their purchases, about 54% of these 1,009 samples or consumers responded with no, they're not comfortable with a drone delivery service. From what we've done so far with notation, then we can assign a p-value to denote the proportion of consumers that are not comfortable with drone deliveries. Remember that p, lowercase p, is the population proportion, and then p hat would be our sample proportion. We learned in Chapter 7 that we can use a sample proportion as a point estimate for our population proportion. In other words, we can find the sample proportion, and then that is our point estimate. We can use that point estimate value to make inferences about our population proportion, or just p. Some important wording in this hypothesis testing is this word majority. When we introduce this word majority, then the majority claim is equivalent to the claim that the proportion is greater than half. So if a majority of samples are answering a certain way, then we can really think of that as p is greater than 0.5. Our population proportion is greater than 0.5 when we connect this to a majority claim. If we were to use majority in everyday language, then that's at least half, right? If a majority of people are thinking a certain way or they answered a certain way, then that's at least half of the people we surveyed. So importantly, majority claim, think p is greater than 0.5. So if we're interested in the majority here for this drone example, then this expression of p is greater than 0.5, that's our symbolic form of the original claim, which is the majority of consumers are not comfortable with drone deliveries. Where did we get this information? Well, we have to be given this sort of claim, right? So this is our example here. Majority of consumers are not comfortable with drone deliveries. With this word majority in our question, then we think p is greater than 0.5. Let's continue talking about some important wording you'll see in this section of hypothesis testing. So the big picture here that we've established is that we have a claim that the population proportion, or p, is greater than 0.5. Where do we get that? Well, we're interested in the majority of consumers. So are the majority of consumers not comfortable with drone deliveries? Then we're really connecting that back to this notation of is P greater than 0.5? Is the population proportion greater than 0.5? Then we're asking, among the 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? We talked about majority, now we're asking about a significantly high number of consumers. In order to answer this, we need to know what the meaning of significance is, and we'll get there. So let's go through some examples first. Let's say out of the 1,009 consumers, we had a result of 506 said that they were not comfortable with drone delivery. To find the proportion here, we take 506 divided by the total number of consumers that were surveyed. So 506 divided by 1,009 is about 50.1%. We got this percentage because then we can see, is that half? Is that greater than half? We'll eventually be able to answer, is that a significant percentage? Is that a significant proportion? Well, from 50.1 and what we know about percentages and proportions, then 50.1 is just barely more than half, right? And half being 50%. So with a percentage like this of 50.1, it's pretty clear that 506 consumers is not a significantly high number of consumers. What about surveying 1,009 consumers again, but now we get a result of 1,006 consumers are not comfortable with drone deliveries. To find the percentage again, we can take 1,006 divided by 1,009, multiply that by 100 to get that into a percentage. That's 99.7%. Now, it might be hard to tell at this point because we haven't quite yet defined this meaning of significance here in Chapter 8. But with such a high percentage like this, 99.7%, we can pretty clearly say that 99.7% is clearly significantly high. Okay, so we gave examples of 506 out of the 1,009 consumers. We gave an example of 1,006 out of the 1,009 consumers. But let's go back to our example here. We want to know about this result of 545 consumers out of our 1,009 because we were given this number of 54.0% of consumers are not comfortable with drone delivery service. Going back to the question here, how do we get 54% and 545? Well, that was given to us in the question. We could have also figured out 54% by taking 545, the number of consumers we're interested in, divided by 1,009, multiplied by 100. So for our specific example, with our specific amount of consumers, so 54%, we're really asking, is 545 consumers a significantly high number of consumers? What we know so far is we surveyed 1,009 people total, so then about 54.0% said that they were not comfortable with drone delivery service. Then we need to decide, is this 54.0% of consumers considered significantly high or not? Well, in order to answer this, we really need to know our meaning of significance here, and we also then can use the methods we're going to talk about in Chapter 8. So essentially for questions like this, we're going to use the method of hypothesis testing to then answer this kind of question. Now, I mentioned we need to know what significance is here, so let's talk more about this. I mentioned that hypothesis tests are also called tests of significance. We've seen this verbiage before, so in section 4.1, we use probabilities to determine when sample results are significantly low or if they're significantly high. Now in Chapter 8, in this chapter, it will formalize those concepts we learned previously in a unified procedure that is used often throughout many different fields of application. In chemistry, biology, social science, finance, all these different fields use hypothesis testing to then validate their data or to maybe say their hypothesis is incorrect if they have to reject their hypothesis about their data, about their population. As a refresher of what we've seen before in 4.1, well, we did see this idea of a significantly high number of successes and a significantly low number of successes. In order to look at significance in the past, we have then found the probability and seen if it's less than or equal to 0.05. If we went through the process of finding the probability and it was less than or equal to 0.05, then we said that that number of successes was significant. And then depending on what X value we were using, we could then say was that a significantly low number or a significantly high number of successes. It just depended on the total number of successes we were looking at and our specific X value here. So again, what this came down to was finding the probability of that certain situation. If it's less than or equal to 0.05, then we did have significance. Now, in order to develop a hypothesis about our population, we have to go through some important terminology on the different kinds of hypotheses. The first kind you need to be familiar with is the null hypothesis. We denote the null hypothesis by H naught, or H sub 0. You'll probably hear me refer to this as H naught. So our null hypothesis is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. So let's say we claim the population mean is 12.1. Then our null hypothesis would be that, yes, our mean is equal to 12.1. It's just a hypothesis, it's just an inference that we're making, and then we can go based on that to decide if that's true, if we accept the hypothesis, or if it's false. And we reject the hypothesis. So we have a null hypothesis. With the example I just mentioned, is that we're saying the population parameter, which in this case we're choosing a mean, is equal to 12.1. That's my null hypothesis. The other terminology now is the alternative hypothesis. So how we define the alternative hypothesis is denoted as H1 or HA. So you can see it as H1 or HA, with A being either a capital or a non-capital letter. And the alternative hypothesis is a statement that the parameter has a value that somehow differs from the null hypothesis. So if my null hypothesis, again, is that the mean is equal to 12.1, then the alternative hypothesis is that the mean is equal to anything else other than 12.1. And again, we can call the null hypothesis H0 or H naught. For the alternative hypothesis, we can call this H1 or HA. So in setting up the alternative hypothesis, if our mean value, for example, again, is anything other than 12.1, then how to denote this properly with our alternative hypothesis is by using these different symbols. So is it less than, is it greater than, or is it unequal to 12.1? In the example I've been using so far, that the null hypothesis is that the mean is equal to 12.1, then my alternative hypothesis is that the mean is unequal to 12.1. So it's equal to anything else other than 12.1. So for the alternative hypothesis, get really comfortable reading these symbols. So less than, greater than, or unequal to, or not equal to. Now in 8.1, we're going to go through each of these steps in the procedure for a hypothesis test. I will describe each step in detail, then we'll go back to that drone example and then apply these steps to that drone example as we go through this section. I won't read all these to you, but do know that when we get past step 5, we can either go the p-value method or the critical value method, and then we meet back up for step 8. So you have this flowchart in your student outline, and again, we'll go through each step in detail, and then we'll apply it back to that drone example. Let's talk specifically about step 1, step 2, and step 3. So in step 1, we will identify the claim to be tested and express that in symbolic form. And again, the format of this section is we'll talk through each step, then we'll apply each step to our drone example from the beginning. Step 2 is give the symbolic form that must be true when the original claim is false. We'll practice doing this. Step 3, consider the 2 symbolic expressions obtained so far. That is, again, to consider what was done in step 1 and step 2, to then form our alternative hypothesis, or H1, and to decide what's our null hypothesis, or H naught. You should get really comfortable working with the definitions of an alternative hypothesis and a null hypothesis. And again, we decide our null hypothesis, then the alternative hypothesis is anything else. What you'll start to see is that our null hypothesis, or H naught, is that the p-value equals a certain value. Or the example we've used in the past is that our mean value, our mu, equals a certain value. Therefore, then, the alternative hypothesis will be any other value, other than the null hypothesis value. So in a null hypothesis, we will use inequality. Then in the alternative hypothesis, this H1 will be the hypothesis not containing inequality, and equality meaning an equal sign. So what you will see then in an alternative hypothesis is a less than, greater than, or unequal to, or not equal to symbol. Okay, so this is how we'll start to form these hypotheses and what to keep in mind when recognizing which is the null hypothesis and which might be the alternative hypothesis. Null hypothesis, you'll see an equal sign. Alternative hypothesis, you'll see less than, greater than, or not equal to symbols. Okay, now we've talked about steps 1 through 3. Let's go back and apply that to our drone example. To remind you about the claim here, we have the majority of consumers are uncomfortable with drone delivery. Okay, so keep this claim in mind. The majority of consumers are uncomfortable with drone delivery. Now let's go on to step 1. And again, step 1 is to identify the claim to be tested and express it in its symbolic form. Remembering what we talked about for the definition of majority, then we're going to use P to denote the probability of selecting a consumer uncomfortable with drone delivery. So P, again, is the probability of selecting a consumer uncomfortable with drone delivery. So then the majority is uncomfortable with drone delivery can be expressed as P is greater than 0.5. The probability of selecting a consumer that is uncomfortable with drone delivery is greater than 0.5. Now let's try step 2. So give the symbolic form that must be true when the original claim is false. So the original claim, again, is that the probability is greater than 0.5. Then what's the symbolic form that must be true when this claim is false? Or other words, the probability is less than or equal to 0.5. Right, so again, here's our original claim of P is greater than 0.5. If that's false, then every other option has to be encapsulated within this notation here. So on this hand, if P is greater than 0.5, then if that's false, then P has to be less than or equal to, don't forget that part, of 0.5. It's really important that this is less than or equal to, right? Because we have to contain all of the numbers here, all of the possible numbers in our probability. As a reminder of how to read these symbols, P is greater than 0.5, and then over here, what must be true for step 2 is that P is less than or equal to 0.5. That was applying steps 1 and 2 to our drone example. Now let's apply step 3. So we'll do step 3 in 2 parts. We're going to identify the alternative hypothesis, or H1, and identify the null hypothesis, H0. Remembering our definition of alternative versus the null hypothesis, the alternative hypothesis is anything other than our claimed value. From step 2, we knew our 2 notations where P is greater than 0.5 and P is less than or equal to 0.5. The trick, again, to identifying the alternative hypothesis is to look for the one that does not contain the equality. So here, equality is not represented by a true equal sign, but it's seen in this notation here. So less than or equal to. In other words, less than or equal to also contains an equality, right? As would greater than or equal to. But here, this one of P is less than or equal to 0.5 does contain the equality. What's recommended here in step 3 is to write out our notation from step 2, then to identify the one that does not and the one that does contain the equality. Then after we've identified which notation does contain the equality and which one does not, Then we go to this step. So of those two expressions, P is greater than 0.5 does not contain the equality. The notation that does not contain the equality becomes our alternative hypothesis. Therefore, putting this all together, H1, our alternative hypothesis, is P is greater than 0.5. So again, for this part of step 3 in identifying the alternative hypothesis, write out our two notations from step 2, then figure out the one that does not contain the equality. That's for the alternative hypothesis. Now let's talk about the meaning of the null hypothesis. So try to write this out very clearly for yourself as well as you go through this. So for the null hypothesis, H0 is the null hypothesis. It's the symbolic expression that the parameter equals the fixed value being considered. Extremely importantly, for the null hypothesis, we will have a true equal sign. For the null hypothesis then, in our drone example, H0, the null hypothesis is P is equal to 0.5. Backing up here to the alternative hypothesis, when we mentioned that the alternative hypothesis does not contain the equality, how we interpret equality here is this meaning here by less than or equal to. But here for equality for the null hypothesis, this contains a true equal sign. So here our alternative hypothesis is that H1 is P is greater than 0.5. Our null hypothesis then, H0, is that P is equal to 0.5. Note that we did not use all of our notation. So from step 2, we didn't end up using this P is less than or equal to 0.5 in determining what's our alternative and what's our null hypothesis. Okay, so keep that in mind moving forward, how we went from step 1 to step 2 and now to step 3 in figuring out our different hypotheses. Let's talk about step 4 now. So the significance level, or alpha, you have seen this before in chapter 7. So now in the context of chapter 8, the significance level, alpha, for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. So again, alpha, our significance value, is the probability value used to distinguish between whether we have significant evidence or not against our null hypothesis. We will practice with these alpha values to make this definition more clear. So, by the nature of this alpha value, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when the null hypothesis is true. What does that mean in notation we're used to seeing? Well, the significance level, alpha, that's really equal to then the probability of rejecting the null hypothesis H0 when the null hypothesis H0 is true. Okay, so we'll talk about how to solve for alpha, but keep in mind this meaning here that alpha is really the probability of rejecting H0 when H0 is true. So when deciding how we select our alpha value, our significance value, keeping in mind that the significance level alpha is the same alpha we saw in 7.1. And remember, we used alpha to find our critical values of z subscript alpha over 2 and t subscript alpha over 2. So common choices for alpha are 0.05, 0.01, and 0.10. What do these correspond to then again for our confidence levels? Well, remember that our confidence level and our alpha value are complements of one another. So for an alpha value of 0.05, that's really confidence level of 0.95 or 95%. Similarly here for 0.01, that's really 0.99 or 99%. Then similarly again here, 0.1 for an alpha value is actually 0.90 for a confidence level, so that's truly 90%. We knew this from chapter 7, where 0.05 for an alpha value, which corresponds to a confidence level of 95%, that's the most commonly used. Before we proceed with chapter 8, I want to go back and remind you on that meaning of alpha. So we saw this diagram in chapter 7. We wanted to find our alpha over 2 value here. We did this by taking our confidence level, then 1 minus the confidence level. That's our alpha value. Take alpha over 2. That was 0.025, for example. Then 1, the total area under the curve, minus this area here of alpha over 2. Then we find this cumulative area from the left. Then we find the critical value that corresponds to this cumulative area from the left. Focusing on just alpha now, what we really saw is that alpha over 2 was this green area here, this green tail here. Alpha over 2 was also symmetric, so it was this area here. In chapter 7, we saw diagrams like this. We could say that alpha was just 2 times alpha over 2. So alpha in total was this area, alpha over 2, plus this area here. Right, so our whole idea of alpha was this area plus this area for a cumulative area of alpha. Now in chapter 7, we saw that alpha was split up. So we took alpha over 2 and it was on the left tail of the distribution and on the right tail of the distribution. Well, what you'll see is that alpha isn't always split up like that. It's not always alpha over 2 over here and alpha over 2 over here. Sometimes alpha is all together in one concentrated area under the curve. For example, here we have alpha all concentrated on the left tail of the distribution. Similarly here, alpha is all concentrated on the right side of this distribution. So from chapter 7, we saw this meaning of alpha, but also know that alpha can refer to an area on one side of the distribution. This will come back as we continue on in chapter 8, so alpha split up into 2 tails and alpha also on 1 tail. Okay, let's continue on now to step 5. Step 5 is identifying the relevant test statistic. So again, we're finding the test statistic in step 5 that is relevant to the test and determine its sampling distribution. So far, we've seen sampling distributions of a normal distribution. We've also seen a t-distribution now in chapter 7. We have not yet talked explicitly about this chi-squared. So here's the symbol for chi. So we have not seen a distribution for a chi-squared distribution. Depending on the question we're asked, then we'll use this table I'll show you to figure out what corresponding sampling distribution and what corresponding parameters we should look into. This is table 8.2 in your book, so when we're specifically dealing with a population proportion, P, as our parameter, then we follow along on this row. So we determine the sampling distribution as a normal distribution. Remember, for a standard normal distribution, we use z values as our x-axis in that distribution. So if we have a proportion, then we connect that to a sampling distribution that's a normal distribution. With this normal distribution, we need to check the requirements. So we need to see that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Then still part of step 5 is figuring out this test statistic. Again, if we have a proportion, we need to check the requirements of a normal distribution. Then we proceed on to calculating our z value with this equation. Because our drone example uses a proportion, we will practice doing this equation. Now let's say we weren't interested in a proportion value, but instead we are interested in a mean value. For a population mean or mu value, we can have either a t sampling distribution or a normal distribution. How we decide which one we're working with, if we're looking at a population mean value specifically, comes back to either knowing the population standard deviation or sigma or not knowing this sigma value. For a sampling t-distribution, it's when sigma is not known. And beyond that, we have to have a normally distributed population or the sample size n has to be greater than 30. Now, if we're working with the population mean or mu and sigma is known, the population standard deviation is known, then we work in this row. We say we have a normal distribution. then sigma is known and we have a normally distributed population again, or again, sigma is known and our population size is greater than 30. Coming to this last column now of calculating the test statistic, again, depending on which row you're in, you'll use a different formula to either calculate T or calculate Z. We calculate T if our sampling distribution is a T distribution. We calculate Z if our sampling distribution is a normal distribution. The next possibility is that we're interested in a standard deviation sigma or population standard deviation. So either standard deviation or variance, where variance is just sigma squared, so the standard deviation squared. This is the kind of distribution I was mentioning we haven't talked about yet, so a chi-squared distribution. For questions like this that are interested in the population standard deviation or variance, then we have a stricter requirement here. So we'd have to go back to chapter 6 and very strictly see, is this distribution a normal distribution? Then if this is the case, if this is the row we're working in, then the test statistic we're calculating is chi-squared. The formula for calculating chi-squared is seen here. I wrote under student outline a challenge. Can you assign what each of these notations mean? And can you do that by memory too? So try to give that a shot. Okay, so we set the stage now. Let's go back and apply some of these things to our drone example. Speaking of notation, I put this reminder here as well. So recall that when symbols are used above a letter, such as X bar and P hat, they represent statistics and not a parameter. Recall that statistics describe a sample and parameters describe a population. Just another reminder here to keep in mind because we've introduced a lot of notation so far in the course. So going back to our drone example, the claim that P, the probability, is greater than 0.5, that's a claim about the population proportion, right? So it's a certain number of consumers out of our sample that either are comfortable with drone delivery or they're not. So in deciding what test statistic to calculate, the only information we need to know is that we're working with a proportion, not a mean, not a standard deviation, not a variance. So here's this row we're going to look at. We're going to treat this sampling distribution as a normal distribution. Then because we're doing so, we need to check these requirements. Then once we check these requirements, then we'll use this formula to calculate our test statistic of interest. And because we're working with a proportion here, then our test statistic of interest is Z. Let's recall what we know. So N is our sample size, that's 1,009 consumers. As we're figuring out these requirements, we need to assign what is P and what is Q. So we can say that P, our probability of success, is 0.5. Then we've done this before, so how we find Q is we take 1 minus P, so 1 minus 0.5, that's also 0.5. Now we can check this requirement to then say, is this truly a normal distribution? If it's not, then we couldn't proceed on to then calculating the Z value. So N times P, 1009 times 0.5, that's about 504.5. So that is greater than or equal to 5. Because my P and Q value are the same, then I don't need to do this calculation again. I can just say that yes, N times Q is also greater than or equal to 5. So importantly, we check these requirements because we're dealing with a population proportion. So we want to see if we can truly treat this as a normal sampling distribution. So far in step 5, we've checked off these requirements. This is a normal distribution. We can treat it like one and then calculate the Z value. Before we calculate that Z value, I want to clarify this meaning of a proportion. We've seen this a bit throughout the semester, so I want to give you this definition. So in statistics and in daily life, a proportion is a part, share, or number considered in comparative relation to a whole. Some examples of a proportion would be that we have 1 yellow marble amongst 3 marbles. Or over here, we have 2 yellow marbles amongst 6 marbles total. Another example of figuring out a proportion amongst relation to a whole is we could say that a portion of the animals at an adoption shelter, some portion of those are dogs. Okay, so I wanted to clarify that meaning of proportion in case you're wondering, how do I know that that was a proportion that we're asked about in our drone example? So again, think of proportion as a part or share of a whole. So for our drone example, we were looking at just a proportion of our 1,009 consumers. So the steps blur a little bit, so now I'll move on to step 6. In step 6, we're going to find the value of the test statistic and then the p-value or the critical value, depending on which branch we want to take on step 6. Remember where we left off from step 5 with our drone example? We were about to calculate that value of z, so we'll come back and do that in step 6. But first, some important definitions from step 6, so one being the test statistic. Before going through the formal definition, here's our test statistic, right? So here's the column. Once we decide if we have a proportion, mean, or standard deviation or variance, then we figure out which test statistic we need to calculate for that certain case. So a test statistic is a value used in making a decision about the null hypothesis. So the formula for these test statistics is more complicated, but know that why we're calculating that value for a test statistic is in order to ultimately make a decision about the null hypothesis that we established. You saw all those formulas, and what we're doing to find these test statistics is converting the sample statistics where we have p hat, x bar, or s to a score, such as a z-score, t-score, or chi-squared score. Remember what these symbols mean again, so we're taking a sample statistic, such as a p-hat value or a sample proportion, such as an x-bar value or a sample mean, and such as an s or the sample standard deviation. The one symbol that's not included here is our sample variance. Remember, that's s squared. In converting the sample statistic into a score, which we'll do in step 6, we will do so with the assumption that the null hypothesis is true. Let's do this now for our example. So we have a claim made about the population proportion, or lowercase p. We had our total number of consumers, that's 1,009. We were asked about 545 consumers specifically out of that 1,009. So in assigning this meaning of an x value, that's our value of interest. Then we've already sort of done this next step, but we're going to find the sample proportion, or p hat specifically. Now, this should be fairly intuitive, but if you want to think of it in this way of an equation, you can do so. So we're going to find p hat, the sample proportion, as our x value of interest divided by the total number of samples. So here that's 545 out of 1,009, that's 0.54. If we wanted to convert that into a percentage, we definitely could. We could take 0.54 times 100% and get 54%. Now, for our p hat value, we do not want to convert that into a percent. We want to keep that in its decimal form. So formally, we find the p hat by taking our value of interest divided by the total number of samples. Here, for this case, we get a p hat value of 0.54. Now, keeping in mind what we're doing now is calculating that z-score. So we need to figure out all the variables involved in that formula. So let's keep going now. With the null hypothesis, or H0, just as we're getting more familiar with what's H0, what's HA or H1, remember that we define our null hypothesis as the parameter equals the fixed value being considered. In other words, it equals the fixed value of interest. We figured out from step 3 that our null hypothesis H0 is P is equal to 0.5. Remember, within step 6, we're working with the assumption that the null hypothesis is true. So I wanted to remind you about that before we proceed on with the calculation. Okay, so again, here P is equal to 0.5. We're working with the assumption that that null hypothesis is true. From there, we can calculate our value of Q. So Q is equal to 1 minus P. Or in other words, P plus Q are complements of each other. They total up to 1. Here, in this context, P are the people that are uncomfortable with drone deliveries, where Q would be the people that are comfortable with drone deliveries. We found our P hat value, which is different than our P value. So we found P hat is equal to 0.54. Remember, P hat is not in a percentage, it's in its decimal form. Now it's time to calculate for Z, so we can do that with the formula that's in table A2 that we've seen on a couple slides ago. That formula is seen here, so Z is equal to P hat minus P all over the square root of P times Q divided by N. Let's plug in the values that we know here. So 0.540 is our P hat value, minus P, which is 0.5. We got 0.5 by assuming that our null hypothesis is true. Remember that we established our null hypothesis as P is equal to 0.5. Continuing plugging in what we know, we take the square root of P times Q over N, so that's 0.5 times 0.5, all over N, the total number of samples, the total number of consumers. If we plug those values in, we're really careful about what we're putting parentheses around, then we should get a value of 2.54. Now, actually, instead of getting a value of 2.54, we can do something to make our answer more accurate, and we should do this in our calculations. What we need to do specifically to make our value just slightly more accurate is to use this full fraction of 545 over 1009. We're using that in place of 0.54. Why would we do that? Well, 0.54 is a little bit rounded, so if we use this full fraction, we'll get a slightly more accurate answer, and we should do this. We should use the full fraction instead of this rounded value for P hat. So again, here's our equation. Here's the values we'd put in, except now instead of using this rounded P hat value, we're going to use this fraction here of 545 divided by 1009. When you replace 0.540 by this true fraction, then you should get an actual value instead of 2.54 of 2.55. Yes, they're very close, but this is more accurate. This is the value we should work with. Okay, so that was part of step 6 in finding our test statistic. We just calculated that. We need to calculate the Z value because we're specifically working with a population proportion in our drone example. The next part of step 6 is this critical region. So the critical region, which you can also think of as the rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Okay, so in our distribution, we have a certain part of that distribution where we would accept the null hypothesis. Then the critical region, or in other words, the rejection region, is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis that some certain value is true. Remember that in our case, for our drone example, our null hypothesis is that P is equal to 0.5. Okay, I also put this reminder here. Recall that the null hypothesis, or H0, is the symbolic expression that the parameter equals the fixed value being considered. Okay, so keep this definition in mind because it directly relates to how we determine our critical region or rejection region. Now, I mentioned you'd see this again in chapter 8 as we were talking about different definitions of an alpha value, a significance value. So as part of step 6 in figuring out our critical region, we have 3 different options. The first is we can have a two-tailed test. When we have a two-tailed test, the critical region is in the 2 extreme regions or tails under the curve. How do we visualize this? Well, this should look familiar to what we've seen before, where we have a normal distribution, then we have this area here on the left, and this area here on the right. In other words, we have 2 tails. The next category of a critical region is working with a left-tailed test. Here, the critical region is the extreme left region or tail under the curve. What does this look like now? Well, here, all of this tail is focused on this part of the distribution. So it's focused in the left tail of the normal distribution, and we don't have any shaded green area here on the right. It's all focused on the left-hand side. Then similarly, we can have a right-tailed test. That's when the critical region is in the extreme right region or tail under the curve. How do we visualize that now? Well, we have our distribution, and then this green region is focused on the right side of the distribution. We'll talk more about how we figure out what tail test to use. Here's a big hint right here that's helpful in determining which test to use. So when our alternative hypothesis H1 has an unequal sign, then we use this sort of two-tailed test. Furthermore, if we have an alternative hypothesis H1 with a less than sign in the symbol notation, then you can think of that as pointing towards the left, so we have a left-tailed test. Another way to think of that is if we have a value that is less than, then we're thinking of values on the left-hand side of the distribution. Then conversely, if we have an alternative hypothesis with a greater than sign or a sign that points towards the right, then we have a right-tailed test. How does this also make sense as far as less than or greater than? Well, this is a greater than sign, and these values are increasing as we go towards the right on the z-axis or the x-axis. In other words, we have smaller values here for our x values, then we approach the mean, then we get larger x values here on the right-hand side of the distribution. So in the case that our alternative hypothesis is less than a certain value, we're looking on the lower end of the distribution. Then in the case when we're looking at an alternative hypothesis that is greater than a certain value, then we're focused on this right-hand side of the distribution. Now, to remind you about the procedure for hypothesis test, we're still in step 6. In both branches of step 6, we're going to find the test statistic, which we've done so far. Now, for example, we found that value for z. Then we can either find the p-value, or we can go this route and look at the critical values. I wanted to first remind you of this broader picture of the steps before we continue on with step 6.